Hello. Hello, Lucia. How are you? All good. Same here. Ready for a stream. Didn't do this contest. All right, so let's go over it together. And so I did pretty well on this one. Even though I got I got a little bit trolled by Q2, not gonna lie. Top 100. Yes, I'm right now I'm at 78th. But the results are not final yet, I think. I don't know. But yeah, I got a little bit trolled by Q2. We're gonna see that in a minute. I had trouble understanding what the question was asking, and I think it was kind of intentional to make it confusing, because it's essentially a very easy problem, but it's, I don't know, I feel like they try to make it harder than it really is by making it confusing. And anyways, let's get started. So not great then. Yeah, that's not fair in my opinion. So Q1, it's another medium, right? This trend of not having an easy as Q1, they've been doing this quite often lately, and this week on it was the same for the bi-weekly, right? On that day. So that day there were 2 contests and none of them had an easy problem. So I don't know. Anyways, it's called transform array to all equal elements. You are given an integer array nums of size n containing only 1 and -1 as and an integer k. You can perform the following operation at most k times. Choose an index I, multiply both nums of I and nums of I plus 1 by -1. Know that you can choose the same index I more than once in different operations. Yeah, this is kind of weird, right? Because why would you... This note is kind of confusing, right? Because why would you choose the same index more than once, right? If you do it twice, then you multiply by -1 twice, which is the same as multiplying by 1, right? So it doesn't do anything, right? So it's kind of, this is already trying to confuse you, I think. I mean, it's something that you need to figure out, right? That it doesn't make sense to do, you either do 0 or you do 1 operation for each I, right? Doesn't make sense to do more than one. Return true if it is possible to make all elements of the array equal after at most k operations, and false otherwise, okay? And here we have 2 examples. The first one we can, and the second one we cannot. Okay. And well, and the size is 10 to the 5th, right? All right, so let's go to the whiteboard to think about this. So this is a common pattern. This kind of idea, well, this kind of idea where you're making some kind of operation, some transformation on like a window. Here the window is size 2. Sometimes you have different sizes of windows. But yeah, so the first thing that you need to think about here is that, so there are only 2 values, right? When you multiply by -1, you change, so you only have 1 or -1, right? So, and you have to make them all equal. That's your goal, right? So you can, your target, you can make them all equal, and you can try both possibilities, right? There are only 2 possibilities. Your target is either 1, or your target is either or is -1, right? So, but if you define the target, right, and you may make a function that receives the target, and you call it for 1 and for -1, right? And if you can for any of them, then you're done, right? But it's easier if you have a target, all right? So anyway, so let me show you another idea. So let's say you're considering position I, right? And there is some number here, 1 or -1, right? But so notice that there are 2 ways of changing this this position, right? You can either change it by doing the operation at I -1 or at I, right? And so it is not clear. So you have to, so if x is equal to the target, so if x is equal to the target, then you don't know if, so it could be that you want to do both, right? Because if you do both, then you multiply this by -1 2 times, which is the same as not doing anything. Or it could be that you don't want to do any of them, right? So it's still, so I still don't know, so I still have options, right? And if it is different, than target, then it could be that I have to, so I have to do exactly one of these 2, but any of them could be possible, right? It could be that I have to do it on I -1 or on I, right? So in the other case, I also don't know, right? But here I is special, right? Because there is an I -1 only because I is not the first one, the first position, right? So sometimes in problem solving, there is this strategy called the extreme principle, which is like a common sense idea that sometimes you have to pay attention to the extremes, right? Because sometimes the extremes are more constrained, as it is the case here. So if you go to position 0, then there's only one way to change position 0, right? You have to do the operation at 0, right? That's all there is to it, right? So if here you have x, then if x is equal to target, then you cannot do operation at 0, right? But otherwise, so if x is different than target, then you must do, right? You must do operation at 0. So it's forced. If you look at the first element, of course this is symmetric, right? It would be the same for the last one, right? But so that means that if you go to the first one, then it's forced. And once you do whatever is forced, right? Now the first element already, it's going to match target, right? And then you can think about the rest of the array as starting from position 1, right? And you're in the same situation, right? Now, since you already did whatever you had to do with operation at position 0, now 1, the position 1 can only be affected by the operation at 1, right? And so again, you have only one option, and so on. So you can do this one by one, and now it's forced. Now everything is forced, right? And when you reach the end, you need to see if whatever, because when you reach the end, you cannot do an operation that starts there, right? So then you have to check that the last element, after you applied all the operations that were forced, you need to check that the last element, so nums of -1, has to be equal to target, right? So this gives us an algorithm. Another thing that you might now notice is that there is something, well, another problem-solving strategy sometimes is to think about the parity of things, right? Whether they are odd or even, right? Just because, and here you can notice that when you do this operation, every time you do this operation, the parity doesn't change, right? Because if you multiply by -1 and the elements are different, right? Let's say they are like this, then they switch, right? So the number of ones and the number of -1s stays the same. Whereas if they are both the same, then they change. If they are both 1, they change, both of them change to -1. So one gets subtracted by 2 and the other one gets added by 2, right? So that means that whether they are odd or even never changes, no matter how you do the operations. And so that means that, so after you do the operations, the one that is not target has to have 0 occurrences, right? The count of the one that is not target has to be 0, right? But that means if the parity never changes, so at the end it has to be even. So it has to be even at the beginning as well, right? Because the parity never changes, right? So we can say, so if nums dot count of minus target mod 2 is odd, then we know we cannot do it. And notice that I don't care how many operations. It doesn't matter if you have an infinite number of operations, you won't be able to do it, right? So we could have, I mean, notice that this condition is not really, it doesn't help, it doesn't make the algorithm faster, right? Because this is already O of n, so we're doing only one pass, right? And when we are counting, we're also doing a pass. So this is just a cool idea that you can, I mean, it's an interesting idea that could be useful in variations of the problem, but in this particular problem, this is enough, right? Well, there is one thing that you can avoid. So if you make this check at the beginning, then you don't need to make this check here, right? Because you know, if only the last one can be different than target, then you know it must be equal to target, right? Because if you know that the ones that are not equal to target are even, you cannot have only one, right? So you can save this check at the end, but again, that's not going to change the time complexity, right? Can you make the width of the browser a little smaller? The end can't be seen. Okay. Like there. I think that's better, right? Can you confirm? No, it's good. You moved it. Okay. Okay, so is it clear? So I think that's the analysis of this problem. So so we can create this function called can with a target, and we pass nums, we pass k, and we pass 1 or k or minus 1, right? So this is the version that has a target. And so we can first do the condition that we said. And then we can go over all the elements except the last one, right? Because we cannot apply the operation to the last one. And here we can ask whether nums of I is equal to target. Well, if it's different, then we apply the operation. We don't need to, I mean, in theory, we would be applying the operation to both, but notice that nums of I it's always going to be, once we multiply it, it's going to be equal to target, and we don't need it anymore, so we don't have to. Yeah, but here we have to check if k is 0, because if we have to do an operation and k is 0, then we cannot do it, right? And here we count the operation, and at the end we return true. But notice that there is a bug in this program, which is that we're changing the input, right? And so here, if we call the first call is going to change the input, and then the second call is going to receive top 100. Nice. Thank you, Glump. Welcome. So here, this would fail, right? Because we would change nums. So we can make a copy here. I mean, we don't need to change it. We could have like a variable, I guess, but we can just make a copy and do it this way. Well, I guess the other way would be better, in the sense that you wouldn't need, so the extra memory would be of 1, but here in LeetCode we don't care that much about that. Cool. So if we did that, yeah, I don't think I like that too much, because we would have, I think we would have, so we would have to have a special case for when there's only 1 or not. No, maybe not. Yeah, never mind. Anyway. Yeah, I think that, so this is so there are hard problems that I've seen, hard problems in LeetCode that are solved with the same idea. Yeah, there were ones where you had like a window of size k, so they gave you k. So here the window is of size 2. There are problems where you have a window of size k, which is a part of the input, and maybe you can, so you subtract 1 to all the elements in the window, and you have to say whether you can make the whole thing zeros, right? And notice that it's the same principle, because there, in order to decrement in that problem, in order to decrement the extremes, right, the first element, there's only one option, right? You have to apply the operation to the window that starts at 0. And so, and you have to apply it as many times as the value of that at that point, right? And so you do that, and then you move on. So it's surprising that maybe this shows how LeetCode is evolving, right? Because this idea would be required for a hard in the past, and now it seems to be required for Q1, right? So that's surprising. Well, progress. Yeah. I wonder. So yeah, for me this was easy because I know this idea, but I wonder how it was in general. So the acceptance rate rate is pretty low, right? So maybe not many people solved it for a Q1. So a Q1 with this low acceptance rate seems unusual, right? Anyways, okay, this is the problem that I think it's surprising. This is the problem that I say it's a troll problem. Count the number of computer unlocking permutations, because I mean the solution is super simple, but it's kind of obfuscated, so it's hard. So well, okay, let me read it. So you're given a complexity array of length n, and there are n locked computers in a room with labels from 0 to n-1, each with its own unique password. The password of computer I has complexity of I. Okay. The password for the computer labeled 0 is already decrypted and serves as the root. Yeah, this idea of naming it the root, it's already confusing. Like, what does that mean? Like, I mean, it just means that it is already decrypted, right? Anyways, all other computers must be unlocked using it or another previously unlocked computer following this information. And here, this is what really confused me, is that here they have 2 bullet points, but they are both saying the same. They are duplicated and they are saying the same thing. But when I was during the contest, I thought, well, if they had 2 bullet points, maybe this is referring to something different, to some different kind of different way of decrypting or something. So you can decrypt the password for the computer I using the password for computer J, where J is any integer less than I with lower complexity. Okay, and this is explained. And now it says the same thing, but let's throw another bullet point. Why not? Just to confuse people. And then it says, find the number of permutations that represent a valid order in which the computers can be unlocked, starting from computer 0 as the only initially unlocked one, since the answer may be nice. Well, and this note is also confusing, because it says, note that the password for the computer 0 with labels for the computer with label 0 is decrypted, and not the computer with the first position in the permutation. This is also confusing because it says not the computer with the first position in the permutation, but it actually is the first computer, because that's the only one that you can. 0 always has to be the first one, because that's the only one that you can use to decrypt the others, and it's the one that is already decrypted. So this also is confusing. Can anyone interpret this? I was completely thrown off by this. Like here it says, so in the permutations they must have 0 at the beginning. So why do they say this? I don't understand. Anyway, so don't get mad. Yeah, I get mad because I wasted a lot of time in this problem. So during the contest, so you can see if you see my code replay, you see you can see that I opened this problem, and then I moved on to, so I wrote the mod, right? Because I have that I usually do that to not forget, and then I couldn't understand it, so I moved on to Q3, and only at minute 28 I went back and I started to write a solution. So I realized what the solution was, right? After I already solved Q3. So yes, I'm sorry if I get mad, but I'm a little bit annoyed. Anyways, so yeah, so here, so yeah, so here the solution. So here you have some number, right? So this is the complexity at 0, right? And notice that, so if you have some computer here at I, what they tell you is that how was the rule? So yeah, so it has to be greater, right? Has to be greater. So that means that if you look at all the, so you look at all the positions, right? And you're gonna have some which are greater than x, right? X is the position at 0, is the value at 0. Right? But what if you have, so yeah, so let me first explain how I got the intuition of to find a solution. So because if you think about an algorithm to solve this, right? This is 10 to the 5, right? In size. And so so here you say, okay, so I'm starting at 0, right? And then I can have any number of numbers that are greater than x, right? Let's say I have this 5 numbers that are greater than x. And so then I can continue the permutation from any of them, right? But then what kind of algorithm, if I had to remember where I'm at in the permutation, then that would make it quadratic, right? And so it seems like something is hard to do, right? If you're trying to count the permutations by making a choice and then having a sub-problem, kind of a DP solution. And so something seems off when you're trying to do this. And so my intuition was there must be some kind of trick. There must be some kind of trick. There must be some kind of way. And so that's when I started to think, so what happens if I consider the first one here that is not such that y is less than or equal to x, right? So for it to be, it has to be greater than x for it to be unlocked by x, right? But let's say that we consider the first y that cannot be unlocked by x. Well, to be unlocked, it's going to need something here that is less than it, right? But since this is the first one that is less than or equal to x, then this one has to be greater than x, right? And so that means that this one cannot be thanks for the follow. So that means that we cannot, so if there is one there that cannot be unlocked by 0, and we consider the first one, we can prove that we can never unlock that one, right? And so that proves that you either can unlock every one of them with 0, which means that any permutation, as long as the 0 is the first, and then any permutation of the rest of the numbers is going to work, or you can't unlock them all at all, right? So that's why I consider this a troll problem. So here, if there's any, so we have complexity of 0, so if we find any other computer with a password with a complexity that is not greater than the complexity of 0, it means that we cannot do it, so we return -1. Otherwise, we just return n minus 1 factorial, right? So that's going to be right? This should be it. Oh, sorry, it's not -1. It means that there are 0 ways, right? So, yeah, I was confused. It's 0. There are 0 ways of unlocking the computers in that case. So this is it. Cool. All right. Q3. Count partitions with max mean difference at most k. You are given an integer array nums and an integer k. Your task is to partition nums into one or more non-empty contiguous segments, such that in each segment the difference between its maximum and minimum elements is at most k. Return the total number of ways to partition the number under this condition. And here again we have to return it modulo 10 to the 9 plus 7. All right. So yeah, this sounds like so whenever you are trying to count partitions, the problem smells like DP, or well, maybe sometimes greedy, but in this case it smells like DP, like dynamic programming, because let's think about it here. So notice that, so we have count partitions, right? So we can define count from some I, right? That can be our problem. This means, so I want to count how many partitions there are starting from position I, right? That would be a suffix of the array. And notice that, so let's say that I have this array. So I have here another 2 and a 3, and here I have a 6, and so on, right? And let's say here's my I, right? And my K is 2. And so notice that if I start at I could have a partition, a part of the partition that includes only the 2, or I could have the both 2's, right? Because here, so notice that the range has to be less than or equal to K, right? And the range is the max minus the min, right? And so, or I could have this 2, or I could have this 2, because now the range is 1, and the range is gonna keep growing, and here the range becomes 4, right? And now it's already greater than 2, and so so it's not true that it could start, that it could go up to there, right? So it has a limit. And so the range, when you start at I and you move to the right, the range, it's gonna increase, right? It cannot decrease for obvious reasons, right? So that means that I could solve this problem by considering the sum. So if I knew what this J was, right? I could go and I could say I could make the count from K for K in range from I plus 1, right? Because the smallest case is when I have only the element at I, and so that means that if this becomes a part of the partition, then I'm starting from I plus 1, the next part of the partition, right? So the count has to start from there, and I want to go up to J plus 1. I mean, if this is Python, right? So this is exclusive, so I want to go up to j inclusive, right? Because this is where I'm starting to count from then on, right? And so this is essentially the recurrence of the DP, right? But there are a couple of problems. Exactly 2 problems. So first of all, how do we find this quickly, right? Because if we go one by one, trying to find j, then that would be too slow, right? So how do we find j quickly? And the other problem is that even if we find j quickly, we're making a sum over this range, right? And that would be linear. And again, that would make the whole thing quadratic, right? And we cannot do something quadratic. So the solution to that is, well, let's see. We can, so instead of doing a recursive DP, we can do something bottom up, and because that gives us more flexibility, because we can keep track of the window of the largest window that has a range that is less than or equal to k, right? And so that solves the problem of doing of finding that j quickly, right? So let me show with code what I'm saying here. So so here we can do kind of a sliding window kind of code, right? Where we have I and j are going to represent our window, and we want to know the range of the elements of our window, right? So that means that we need to know quickly the maximum and the minimum, right? So one data structure that we can use is the sorted list, right? So we can have our window, which is initially empty, and here we add the element we add the element at I, right? And so now that we grew our window from the left, I guess we could call this L and an R, so that if that's clearer. So now that we grew our window from the left, we need to see if we have to shrink it from the right. So while the window, so the last element of the window minus the first element of the window is greater than k, then that means that we have to shrink it, right? So we remove the well, I guess we can pop, right? No, sorry, because no, that makes no sense. We don't want to remove the largest one. We want to remove the one at nums of r, right? And we want to subtract 1 from r, right? We're shrinking the window. And now, so now this solves our problem of how to find j quickly, right? But we still have the other problem. So, but let's forget about the problem for a moment. So here we want to count the ways and so that means that the ways at L is going to be the sum for I in range between L plus 1 and R plus 1. We want, so R is our window inclusive, right? So we want to go up to R plus 1 inclusive. So that means that we need to, here we need to say R plus 2, I think. Yes. And so here we want the ways of this, and we need to mod this. And here we return ways from the beginning, right? This is going to be, okay, so this passes the example. This is going to be too slow, right? Because here, like I said before, we're doing, this is going to be quadratic, right? But notice that we can do, we can do another technique, which is called suffix sums, right? Because we want the sum of a range, right? This is essentially adding a range. And if we have the sum of the of all the suffixes, then we can calculate in O of 1 the sum. So let's call this suff, and this is going to have yeah, we want to have one more so that this makes sense. And so here we want the suffix of L plus 1 minus the suffix of R plus 2, and we want to mod this. And now we have to update the suffix. And so this is going to be just this, right? This is how suffixes array work, right? You have for position L, it is equal to the array that you want to calculate the suffixes, the suffix sums of, and plus the suffix sums of the next element, right? So this should be it. Why did I wrote R plus 1 if I wanted to write R plus 2? Okay. That was a mind fart. Brain fart. Cool. So this runs in 1.5 seconds. No worries. Yeah. So this is a pretty cool problem in the sense that, well, I mean, it's a very technique heavy problem. Nice. I'm not sure I'd have come up with the suffix sums idea during the contest. Well, that's cool because this illustrates. So this illustrates why it is important to learn how to do bottom-up DP, because it allows you to do this kind of thing, right? You cannot do this kind of thing with recursive DP, as far as I know. Yeah, notice that. Yeah, yeah, this is a standard technique for DP. Well, this is what I was saying, that I don't think you can do this top down. Hello, Bobby. How's it going? This is what I was saying, that I don't think you can do this top down. I mean, if you find, because of this reason, right? You need the suffix sum, right? Notice that this is not, so the part of the sliding window is not really necessary. You could do a binary search with some kind of range query for the minimum and the maximum, which one good option is to do sparse tables to get in O of 1 the maximum and the minimum of any range. But yeah, even if you do that here, if you do a sparse table here, so here the operations of the sorted list are logarithmic, and even if I used sparse tables for this, the overall time complexity of the algorithm would still be n log n, because creating the sparse tables is n log n, right? So I don't know. I don't know if there's a way. I don't think there's a way of solving this in linear time. But let me know if you find Bobby, if you find a way to solve this top down, let me know. You can share it in the Discord. And if you find a way to solve this in linear time instead of n log n, then also please share. Because I thought a little bit about it and I couldn't do it. Yeah, sometimes, yeah, maybe I should have looked into. If you don't know, then how would I know? Yeah, no, but maybe because sometimes that's what I was going to say, that I don't look at the editorials and the other solutions as much as I should. So maybe if you find the solution of a top contestant, you can share it, right? Anyways, here's Q4. All right, so minimum steps to convert string with operations. You're given two strings, word 1 and word 2, of equal length. You need to transform word 1 into word 2. For this, divide word 1 into one or more contiguous substrings. For each substring, you can perform the following operations. You can replace, you can swap two characters, or you can reverse the substring. Each of these counts as one operation, and each character of each substring can be used in each type of operation at most once. Yeah, this is interesting. This is related to the solution. So no single index may be involved in more than one replace, one swap, or one reverse. Yeah, this is kind of weird. And it shows kind of the approach of the solution. because notice that it doesn't make sense to do a reverse more than once, right? So you can think about the reverse operation as something that is independent of the other operations, right? Because you can always, if you do a reverse, you can always adjust the indices of the other operations, of the following operations, right? So that they still apply to the same elements. And of course, if you do the reverse operation twice, then it has no effect, right? So here the only information that they're giving you is this, is that the only information that you have to take away from that restriction is that you won't have to do something like, you can't do something like this, like having, so what if you have something like this, right? So this is your word 1, and this is your word 2. And if you could do a swap that involves the same index more than once, then you could do two changes, right? You swap this 2, and then you swap this 2, and you sort it, right? With 2 operations. Right? But you can't do this, right? Because here you're doing a swap, you're doing 2 swaps that involve the same index, right? The index 1, right? So this is not allowed. And this is what makes the problem easier, because if you had to, so if there were no restrictions in the swap, I think this is a much harder problem, because then you have to start. Hebrew, can you do some combinatorics problem? That's you can combinatorics. So you can go into my Discord and share and ask for help on combinatorics problems. So in this stream, I'm focusing on this contest, but I'm open to suggestions for future streams. Okay, so here, so what I was saying is that, yeah, it's a harder problem if you can do swaps without restriction. So, and notice that it's never, so it only makes sense to do a swap if you have this kind of situation, right? If you have something like this, right? It only makes sense to do a swap if you have something like this, where doing the swap just make the characters match. Because the other option, if you had something like this, where one of them match, but then maybe the others don't match, then you would need to do a swap, and that would make the X match, but then you have to change the Y and make it a Z, right? And so, but it doesn't make sense, because you can just do, if you're going to do 2 operations, then you can just change this to z and change this to x with two operations, and you just do the replace operation twice and you're done, right? So the swap is only useful in this situation, right? Because you can solve this in one operation, whereas if you had to use the replace operation, it would take you two operations, right? So that means that once you know what the once you know what the substring, once you make the division of the or the partition of the string, and you know which substrings have to match with which, then it's just a matter of finding all the pairs of this kind, right? And counting how many swaps you need. You need to fix those, and checking if you do the reverse or not. And then whatever is left unmatched, then you have to change it with the replace operation, right? And that's going to give you the optimal number of operations, right? So we could start by doing that, right? Like mean cost. So if we know if we know what the substring is, right, we can say, okay, we have word 1 and we have word 2, and we want to find the minimum cost of matching them, right? So so we know we want to let's try first without the reverse, and then we try again with the reverse, and we keep the best, right? And so now we want to count. We're going to count how many operations we need of swaps and replaces. So base is going to be whether we reverse or not, right? So it's going to be either 0 the first iteration or 1 the second iteration after we do the reverse. And after we calculate this, we're going to keep the minimum, right? And so now we want to count. So we're going to go over the corresponding characters, and if they are equal, then we don't need to do anything. But if they don't match, then we have to see if there is if we have the opposite of this, right? Because if we have the opposite, if you have at least one occurrence of the opposite, then we can do the swap, right? So if we have this, we just subtract 1 from it, and we add 1 swap to the operations. Otherwise, we just count it, right? And so that's going to make us deal with all the swaps, and now we are left with the replaces, right? And those are going to be the sum of the values, right, of the counts, right? Because we only added corresponding characters that were different, and we removed all the ones that we swapped, and so the ones left are the ones that we have to replace. And so this solves our problem. Right? Do you agree? So this is the minimum cost, and we want to cache this so that if it's called more than once, we don't do it more than once, right? And then the partitions is just the same as the previous problem, right? It's the same kind of DP. Mean cost partition. So this is the same as the previous kind of algorithm, right? If I so yeah, maybe we can save this here. So if we are done, then we don't have anything else to match. But if we are not, then we have to consider matching matching this, and so we want the minimum of the mean cost that goes from I to j plus the mean cost partition from j, right? Right? And so now we can call this, and then we cache clear. Remember that you need to do this because there is a bug on LeetCode that counts the memory of all the test cases that your program is not using anymore. It still counts it as being used, and it can throw memory limits exceeded. Yeah, and this we cache this as well, right? And this is it. And this is it, and it runs in 1 second, so that's fast enough. So yeah, I think this wasn't too bad. This for a Q4, I think. I might have spent more time on Q2 than on Q4, maybe. Well, I spent like 20 minutes in Q4, and who knows how much time on Q2. Well, how much time did I spend on Q? Yeah, so I spent like maybe 15 minutes in Q3. So 20 minutes for Q1 and Q2. Yeah, and Q1 was probably yeah, 4 minutes or something. So yeah, I spent like 15 minutes in Q2 and 20 minutes in Q4 and 15 minutes in Q3. So yeah, it's kind of, it makes no sense the time on Q2. All right, so I think that's it. I hope you learn something from this, and you realize that Q4 wasn't such a big deal, right? And I think Q3 might be even a little harder because it required all these techniques. Thanks for the follow. It required more tricks that maybe are a little more advanced. Well, I mean, this required understanding, making a few observations about the operations, right? The thing that I said here, that it's always better to do a swap, right? Anyways, so that's all I have. So thanks for watching. Remember to join my Discord. Q4 sounded more scary. Yeah, but it's not. Yeah, when you read it, it seems like there's a lot of stuff going on, right? Because there's you're doing the partition, and then you're doing these operations, and seems like you can do them in any order, and it's complicated. But once you when you think about it, you realize that it's not a big deal, that it's kind of simple. You can break it down like this. Yeah, maybe something that I did not say is the constraints, that the size is 100. Yeah, I forgot to mention this. That's why I knew that this kind of algorithm that is n cube was good enough, right? Yeah, I forgot to mention that's crucial. Yes, of course, when I saw this during the contest, I did see this, and that's why I realized that I was thinking about this kind of solution, where you reduce this to, you do this kind of thing, and you reduce it to solving it linearly for a substring, right? And that gives you an n cube algorithm. Yep. All right. So see you on the next one. Bye bye.